Hello. So this is a continuation of an earlier video about empirical probability. We're going to look at a problem with a little more complicated data and get into mutually exclusive and not mutually exclusive and how those two things differ. All right, so first take a look at this table, maybe pause the video, get your brain into it. It's always a good way to start before I start talking so you have your own ideas about what's going on. All right, so if we select one person from this population of um, people ages 15 or older in the US in 2010, so all the populations are given in millions. So what is the probability that a person is widowed and female? So anyone we pick as our in the group, the top of our fraction has to be both widowed and female. So that's what I'm looking for. Widowed and female right here is 11 million people. And that is going to be out of the total number of people, which is going to be this down here. So this probability is going to be 11 out of 242. And since they're both in millions, it doesn't really matter if we write millions. And you could get the percent if you want. Now we look at, you change one word, we change a bunch of words, but you change and to or, and it's a little bit different. So now I'm looking at married or divorced. So if I look at the total number of married, that's right here. Total number of divorced, that's right there. So married or divorced is the sum of those two things, which would be 154. Again, out of our total for everybody, that's 242. And if you do that math, you get approximately 0.64 or 64%. That's an or. You need both. How about part C? The person is divorced and widowed. So now I'm looking for where both things happen at the same time. And I suppose you could argue that it's possible to have been divorced or have been widowed, and then you are divorced, or then you are widowed. But for our purposes, it's happening at the same time. I suppose if you got widowed and then divorced, it would work. But anyway, those are all really good mathematical questions to ask as we look at this data. What does this mean? So there could be some confusion about this question. You might have to dig deeper into your data, but if we take it sort of at face value that you can be one or the other, is it possible to be both? You would say no, and that would be 0 out of 242, which is 0%. Again, if you wanted to argue that somebody could be, we would have to find that data. We'd have to find a way to break it out. People who had been widowed and now are divorced, or are divorced and then got widowed, because there could be some people in there, but we can't tell from this table how many of those people there are. So our last question here is probability the person is divorced or male. So I need to pause the video and give that your best shot. And now if you're back, I'm very curious about how you did this, because this is one of the probabilities that can be fraught with possibility of error. Because if you do sort of similar to what we did up here in part B, where I add my two totals, so I look at divorced, my divorce total is 24, and my male total is 118. And it would be very, very tempting to add those two up, 24 plus 118, and take that out of 242. And if you did that, you actually would not be correct. You'd be overstating the probability that you're divorced or male. So if that's what you got, I want you to take a minute and think about what you might have missed. And if that's not what you got, hopefully you were thinking in the right track. Because the other way to think about this is we don't think about totals. We could think about, okay, male is 10, are divorced males, 14 million are divorced females. Then we also have male is, there are 3 million widowed males, 40 million never married males, and 65 million married males. And really our total is all of those numbers added up, which is slightly less than our 24 plus 118. So it is not this, but rather 65 plus 40 plus 10 plus 3. And that's all of our males. And then we have to add the 14 million females who were divorced to get that total out of 242. And that turns out to be 132 out of 242, or approximately 55%. Perhaps you're thinking at this point, well, that's a lot of work. Is there another way to do that? So this question in particular is going to lead us into our talk about what I said, which was mutually exclusive and not mutually exclusive. So when we're looking at the union, so we're looking at the or. This doesn't work for the and, because the and is you're doing the intersection, but when we are trying to find the or, how to find the probability of the or. If the two things can't happen at the same time, so that's mutually exclusive, then it's really easy. You can just take the probability that the first thing happens and add it to the probability that the second thing happens, and that's your total probability. But when the events are not mutually exclusive, so when they can happen at the same time, so in our last example, the person is divorced or male. You can be both divorced and male. There's an overlap in those two big categories. Then we can add the two total probabilities, but we have to subtract that intersect. And that would be sort of an easier way to look at this. So if I go back to this right here, so that's this right here, the probability of A or B, you take the probability of A, add the probability of B in total, but then you subtract the probability of that where they happen together. So if we come back here and I think about, so now I can look at, well, here's the probability that we're divorced, or that's the number of ways. So that's the 24 out of the 242. And I can add it to the probability that I'm male. But this is now too high because this has been counted twice. The 10 people, or the 10 million, sorry, people in the US over 15 who were married or divorced and male is counted twice. So what we can do is, instead of this right here, we can re-edit this and say we're going to take our 24 out of 242 and we're going to add the 118 million out of 242, the probability that you are male, and then we're going to subtract that overlapping probability of 10 out of 242. And that's going to get us our same answer that we got up here, which is 132 out of 242. So that not mutually exclusive, that is the thing that we have to watch out for. This guy right here. Mutually exclusive, you can just add them up. Not mutually exclusive, you cannot do that. If you want to think of it sort of in a Venn diagram way, so our probability that we were male, or the number of ways that we're male, was 118. So that would be this whole bubble. The total in the bubble is 118. And if we think back to the divorced, there were 24 million total. So this bubble right here would be 24 million. But then there were these 10 in the overlap. So this is 10 here, which means inside here is really 14, and inside here was really 108. So my one, and that's the 108 plus the 14 plus the 10. You can see that kind of when we looked at this one. My 108 is this and this. Here's my 14. So this, the green is the male but not divorced. The blue is the female divorced, and then the 10 is that overlap. Right? So what's the probability a person chosen is male or divorced? Again, you can see it this way. We would have that 108 plus 10 plus 14 out of the grand total, which would be the outside of the box. All right, so I want you to look back at the table, and I want you to think of two events that are mutually exclusive and then name 2 events that are not mutually exclusive. So I want you to pause the video and think about that, and then find the probability of each of your choices. Okay. So hopefully you're back. There are lots and lots and lots of options, but are mutually exclusive. So that means they cannot happen together. So 2 things that can't happen together are, for example, married, or never married. You can't be, or those are mutually exclusive. If you've never been married, you're not going to be in the married category. If you're married, you're not going to be in the never married category. There's lots of other options you could come up with. 2 events that are not mutually exclusive could be anything like, oh, female and never married. There is overlap. So there's lots and lots of different ways. And then so in mine, the probability that I'm married or never married, I can just add up those 2 totals, 130 plus 74, and it's easy peasy lemon squeezy. I get 204 out of 242. But when I go to do the female or never married, I can't just do the 124, that's the female, plus the 74. I can't stop there because I have counted these people twice, so I need to subtract the overlap. And that would be my answer. So hopefully you have a little better idea of mutually exclusive and not mutually exclusive.